Welcome back to the workshop. We want to continue taking a look at section 2.8, Bayes' theorem. And we're going to take a look at a theorem. It is not Bayes' theorem yet. The next one will be, but this theorem is essentially what we did in our previous example. So if events B1, B2, all the way up to Bk constitute a partition of a sample space, and all of those individual probabilities are non-zero, okay, then for any event A in S, we have that the probability of A can be given by what? Well, in our last example, we said that it could be given by the probability of A, call this A, would be given by the sum of the probabilities of the intersections. But the intersections can be given as products. And so our theorem makes the statement in that way. And we want to add up the intersections with all K of the sets, all the events in the partition. So sum from 1 to K of all of the probabilities of the intersections, but the probabilities of the intersections are given by probability of BI times the probability of a given BI. So that's our theorem. So let's take a look at this using another example. Hopefully, if there was any lack of clarity in the previous example, this one should help make things a little more clear. There is a little bit less going on in this example, but only a little bit less. So I'd like to first, I guess, read the problem. So in a certain community, 9% of all adults over 50 have diabetes, not diabetes, diabetes. If a health service in the community, hospital or whatever, family doctor, correctly diagnoses 93% of all persons with diabetes as actually having the disease, but also incorrectly diagnoses 4% of all people without diabetes as actually having it, we want to find the probability that the community health service will diagnose an adult over 50 as having diabetes. So how can we diagnose someone with diabetes? Well, we can get someone that actually has diabetes and diagnose them as have diabetes. Excellent. We do that 93% of the time. Or we can get someone that doesn't have diabetes and we can still diagnose them as having diabetes. That happens 4% of the time, okay? 93% of people who have it get diagnosed with it. 4% of people who don't have it get diagnosed with it. That's the idea. So if we have a person, yeah, let's go person. Excellent. So if we have a person, one of two things is going to happen, or one of two qualities is true about this person. They either have diabetes or they don't, right? So if we let D be the event of a person having diabetes, then D prime or D complement is the event that they don't have diabetes. And then we're asking what's the probability that they're going to be identified as having or diagnosed as having diabetes. That's what we want to find here. So the tree diagram I find to be quite helpful. So I'm going to continue providing that for our examples, or at least this one. So I suppose maybe before we go too far, let's make sure that we're all on the same page. We want to let B be the event that a person over 50 is diabetic. And let I be the event that they are diagnosed or identified as having diabetes. Excellent. So let's take a look at the probabilities then. What's the probability that someone has diabetes? Well, let's see here. In a certain community, 9% of the people over 50 have diabetes, so that'd be 0.09. What's the probability then that someone doesn't have diabetes? Well, this would be the complement rule, or you could think of it as simply, let's see, thinking back to our introduction of probability, S, the sample space is a certain, it has a probability of occurring of 1, and D and D complement form a partition, so they are mutually exclusive events, and together they give the entire sample space. So it must be 0.91, okay, because those two probabilities added together give us the probability of the sample space, which is 1. So what's the probability that someone is diagnosed as having diabetes, given that they are in fact diabetic? Well, this happens 93% of the time, so that would be 0.93. And what's the probability that someone is identified as being diabetic, given that they're not actually diabetic? Well, that happens 4% of the time. Notice that these do not need to add up to 1 at all, because this would in fact be, the complement of this would be, well, there's several things that are in the complement of this, okay? Not just this thing here. So we got to be really careful about that. These do not need to add up to 1, but these do, because these are not complementary events. All right. So then the probability that someone is diabetic and they've been identified as such is given by the probability that they are diabetic times the probability that they've been identified as such, given that they're diabetic. Excellent. And the probability that someone is not diabetic but has been identified as being diabetic is given by the probability that they're not diabetic times the probability that they're identified as being diabetic, given that they're not. All right, again, the reason that we would write it in this way is because this happens to be the information that we have. Sometimes information is collected in such a way that the result is this. We have these certain percentages or relative frequencies, that sort of idea. And that allows us to estimate percentages, giving us these probabilities or approximated probabilities typically. Okay, so with this, the probability, what's the probability that a community health service will diagnose an adult as having diabetes? Well, the probability that someone is going to be identified with it is the probability that they're going to be identified and they have it, plus the probability that they're going to be identified and they don't. Sorry, I said that backwards. Probability as identified as having it and don't have it, plus the probability of being identified as having it and do actually have it. Okay, but we just said that this is the probability that they don't have it times the probability that they're identified given that they don't, plus the probability that they do have it times the probability that they're identified given that they do. All right, and we have these probabilities. We wrote them down up here. The probability that they're not diabetic is 0.91. Probability of being identified given that they don't is 0.04, plus the probability that they are diabetic. Let's go ahead and redo that. Just get rid of this. I don't need the P anymore there. Probability that they are diabetic, which was 0.09, times the probability that they'll be identified given that they do, 0.93. All right, excellent. So we perform those calculations and we get 0.1201. And we answer the question that was actually asked. The probability that someone, maybe we should say an adult over 50, is diagnosed with diabetes is exactly what we found here, 0.1201. If that answers the question. Excellent. Hopefully that clarified any misconceptions or misunderstandings. If questions still remain, or if something needs to be clarified, don't hesitate to get in touch with me. So we'll move on for now. If you have questions, get a hold of me, and then watch whatever you like to do there. But we've got one more theorem and one more example to consider. So I'll see you guys back in the workshop in just a little bit.